Okay, that's fine, Aiden.
All right, thank you.
Okay. All right. So I'm going to go back to the concept of hybridization again, but I want to talk a little bit more about double and triple bonds because we haven't really talked about how they look in hybridization. We did all these. Whoops, I'm going the wrong way. Sorry. Okay, multiple bonds. Let's take a look at what multiple bonds look like in the hybridization process. We have here the Lewis dot structure for ethene. It shows a carbon-carbon double bond and then single bonds to, whoops, I wanted the pointer. There we go. So we've got our carbon-carbon double bond and then single bonds to the hydrogens. In this case, we need to form 3 bonds. We have 3 electron domains, so we need to form 3 bonds. So we can take this S and hybridize it with 2 of the P's, including one of those that's empty. This is our electron configuration for carbon. That's going to form 3 sp2 hybrid orbitals, each containing 1 electron that can form a bond. So one of those will form a bond between the 2 carbon atoms. Note that is a sigma bond because it lies on the axis between the 2 nuclei. The other 2 sp hybrid orbitals will form sigma bonds with the hydrogens for each carbon. That is also those are also sigma bonds because they lie on the axis between the nuclei. But what we have here is 1 leftover electron in an unhybridized p orbital. That electron is right here in this bilobe structure. Somewhere in this, remember that this bilobe structure is 1 p orbital that is unhybridized. And each of these carbons has 1 electron in it. The bond, the second bond that is forms by the side-to-side overlap between those 2 unhybridized p orbitals. So the side-to-side overlap here above and below between those 2 p lobes, pictured over here as this big area in space above and below the axis of the nuclei, that's the unhybridized p's side by side forming the pi bond that exists as a double bond. Remember I said that all double bonds consist of a sigma bond. The first bond that's formed is a sigma bond. The double bond is a pi bond, and that occurs by this side-to-side overlap. The triple bond that you can see here in acetylene is the same kind of thing, but we now have 2 unhybridized p orbitals. When we hybridize this, our carbon only needs to form 2 bonds, one with the other carbon and one with the hydrogen. So I only need to form an sp hybridization here to form 2 sp 2 hybridized orbitals, or sorry, that's a mistake. This diagram is wrong. It's an sp hybridization. And I can form 2 sigma bonds, one between the 2 carbons and one between the carbon and the hydrogen. Our 2 unhybridized p orbitals then, this is one of them. This is the y-axis p, and this one would be the z-axis p orbital. Those form side-to-side overlap, just like it did with the double bond, only it is above or it's in front and behind the axis of the nuclei. So those are both pi bonds because they don't occur on the axis between the nuclei. So I have actually have models of these here. Here is our the ethane. This is has sp3 hybridization. We have 4 bonds. One of the interesting things that you'll learn in organic chemistry is that this molecule allows free rotation around that bond without disrupting this bond between the two carbons. So that you can get free rotation around that bond without breaking that bond. That's going to have an impact in carbon in organic chemistry when you start talking about polarity, if some of these atoms are not hydrogen. So if any of those atoms, constituent atoms, are something other than hydrogen, it can affect polarity, but not so much on a bond where you have free rotation. The second bond that I showed you was ethene. And this is showing the side-to-side overlap above and below the axis of the nuclei. These, if I show it to you this way, you can see that these carbons are sp2 hybridized because we're forming those three bonds, those three sigma bonds. This molecule is rigid. It cannot rotate, because if I were to try to rotate that bond, I would be breaking the side-to-side connection above and below. So that second bond, that the pi bond, makes this a rigid molecule. And again, when you get into organic chemistry, you'll find that that has an impact on polarity. So that side-to-side overlap is important. The other thing that you should be aware of with this is, I've told a few of you, someone asked a question that led me to point out that there are very few atoms that can form double bonds. Carbon, nitrogen, phosphorus, oxygen, sulfur, those can form double bonds. And the main reason they're forming double bonds between p orbitals. And the main reason there's a very limited number of atoms that can do that is because in order to create this side-to-side overlap, you have to approach each other pretty closely. The atoms can't be too far apart. So bond length is going to affect whether or not you can form a double bond. And so that's why the smaller atoms can form double bonds, but larger atoms further down in higher periods cannot, unless they do it using d orbitals. Then they can do it using d orbitals. And the last one, the linear structure, this is acetylene, and it has two pi bonds, one above and below, and the other in front and behind. This is a linear structure. So that gives you a little bit of a visual of what happens when you have multiple bonds. Was there anything that I wanted to know? I guess that's it. So we'll go from, we're going to move on. Come on. Oh, okay. I guess we're there. All right. Okay. Just there. Okay. So, oops, I'm sorry. I'm paused. That's my problem here. Okay. Actually, come on. I'm sorry, my screen share was stuck. Let's see if we can try this again. It's just stuck. Let's try this again. Okay, there we go. We should be able to go now. Why is it stuck? I don't know. I apologize, guys. I think I'm going to have to close this one. if I can. Nope, it's not letting me do it. I'm going to have to close this out and try again. Guys, I'm sorry, I'm gonna leave the meeting and I'm gonna try to come back. I'm gonna have to stop this because my computer is stuck. So I'm gonna end the meeting and then I'm gonna reopen it. I apologize.